Hello, in this video we are going to continue our Swin attention class, and first we are going to implement absolute positional embedding, and then we are going to extract queries, keys and values from our input tensors and reshape them to the desired shape that we can use in our dot product similarity. Okay, let's start. Okay, the next thing that we need to initialize is this one, which is basically a linear layer, and the input to that is dimension, which is number of channels that we have, and the output is also inner dimension, which is equal to number of channels multiplied by 3. And the reason we are creating this is that we are going to create our query, key and values using the tensor that is we are getting as an input. And then we are going to include our positional embedding. So let's add our positional embedding. For positional embedding, for now we are going to use this line, and this is going to be our absolute positional embedding. Later on we will come back and add relative positional embedding, and this absolute positional embedding, the size of that is 49 by 49, and this is where we define that. So we say here window size to the power of 2 and window size to the power of 2. To get a better understanding of absolute positional embedding, let's look at the VIT paper. So in VIT paper, we can see that when we get an image as an input, the image is divided into patches, and then each patch itself is a token. But when we divide the image into patches, we need to record the information where that patch belongs. For example, this patch is a top left patch, and this patch is a down right patch. So we need to have one mechanism to record the position of the token. That is why we are using a positional embedding. And for VIT, they use absolute positional embedding. Let's look at that. That somehow looks like this. For example, for a patch in the top left corner, this patch, you can see this element here has the highest value. So that's going to tell you that this patch belongs to the top left corner. And you can see as we come to the middle, that yellow spot is going to be in the middle. Or if you go to the right, that's going to be on the right. If you go to the left, that's going to be on the left. If you come here, you can see that this is down right. And this is how absolute positional embedding is going to help us to know where that token belongs in the image. Okay? And this line is going to create that positional embedding for us. After this positional embedding, we need one more thing to be initialized. Let's do that. And that's this one. So this is a linear layer. The input is inner dimension. Again, inner dimension is head dimension times heads, which is basically number of channels we have. And the output is also dimension, which is also number of channels that we have. So we have this called as toOutput. And now we are done with all of the initializations, and we can start creating our forward section of the class. The first thing that we check in our forward function is to see if that block is a shifted block or a normal block. If it is shifted, we are going to send our input tensor to cyclic shift. As we said, it's gonna do the shift for us. And this is the size of input X. Okay, so it is 56 by 56 by 96 for the first stage. For the second stage is 28 by 28 by 192. Third stage 14 by 14 by 384, and the fourth stage is 7 by 7 by 768. And we know that cycle shift is not gonna change the size of our tensor, so output of that is again same size. Okay, now in this line we are just going to get the sizes of the X. For example, the first element is gonna be the batch size, and then we have the 56 here, and for the height and for the width 56, and edge is gonna be the heads for us that we defined here. For example, heads here, you can see we defined here as 3, 6, 12, 24. Okay, so we just use x.shape and self.head to get these variables here that we are gonna use later on in the code. Now let's consider this line. In initialization, we created these two query queue values here, and when we put X as an input to that, because it's gonna multiply that by 3 for the output, here. So we saw that that's going to be multiplied by 3. So the output is going to be this. So this is the dimension of the output tensor. So window sizes don't change. It's still 56, 28, 14, 7. But number of channels are going to be multiplied by 3. And then we are going to use the function chunk and divide it to 3 distinct tensors based on the last dimension, which is number of channels that we have. Okay, and to know more about the function chunk, we can look at the PyTorch website, and we can see here the input is a tensor, and chunk is the number of chunks to return, and dimension is the dimension along which to split the tensor. And it says that if the tensor size along the given dimension is divisible by chunks, which for us it is, all returned chunks will be the same size, and that is what we have, because for us queries, keys, and values are going to have the exact same size. And for example, if we look at the QKV0 size, we will see that that is the exact size of the input tensor that we have, which is going to be the size of our query, key, or value. Okay. The next thing that we want to know is that how many windows we have in each stage. For doing that, we are going to divide an edge, for example, divided by window size, and we get the number of windows in the edge direction. Or for the width direction, we can see the number of windows by dividing the NW by the window size. For the first stage, 56 divided by 7 is 8. So we have 8 windows on the height, and we have 8 windows in the width direction. And for the second stage, we have 4 by 4. For the third stage is 2 by 2, and for the last stage we have 1 by 1. Here we saw that, for example, in the first stage we have 8 by 8, 64 windows. Second stage 4 by 4, 16 windows. Third stage 2 by 2, 4 windows, and last stage only 1 window. Okay. The next thing that we are going to do is to rearrange this QKV. Let's do that. At the beginning, we imported this rearrange function from the Einstein operation library, and now we are going to use this rearrange. Let's do that. Okay, now we are using this rearrange function to rearrange this QKV to our distinct query, key, and values. And let's look at our QKV again. So here we saw that this is the dimension of, for example, one of the elements of the tuple. And we can see at the beginning we have the batch size. So batch size is shown here by B. So that is our batch size. If you remember, we define B here as our batch size from the X shape. And then we have the number of windows that we have in height, which is, for example, for the first stage, it's 8. So we define that here as 8 times WH. What is WH? WH is our window size. We have 7 as our window size. So it's going to be 8 times 7. So it is 56. In a similar fashion, here NWW is 8 for the first stage. 8 times WW. What is WW? That is window size. So it's going to be 56 here. Okay. So we have 1, 56, 56. The next one should be 96. Or as we know, that is the number of head to the embedding dimension. What is the number of head in the first dimension? That's going to be 3. What is our embedding dimension? That is 32. So it's going to be 96. So when we say 96 here, that is basically H, which is 3, times D, which is 32. Okay. Now this is the shape of our input. We are going to convert this to this shape. We actually printed that for Q here, so we can see that here for the values. So the first thing is B, which is batch size. So batch size is 1. Then we have H for the first stage, that's 3. So I get 3 for the first stage. And then I have NWH, that we know that is 8 times NWW. What is the NWW? That is 8 again. So here it's going to be 8 times 8. It's going to be 64. So that's the reason we have here 64. And then we have WH, which is window size, times WW, which is again window size. So it's gonna be 7 by 7 is gonna be 49. That's the reason we have 49 here. And at the end, we have D, which is our embedding dimension, which is 32. Okay, so for the first stage, again, I get B equals 1, H3, NWH times NWW is going to be 64, and then I get WH times WW as 49 and D as 32. For the second stage, I'm going to get this. B is 1, H is 6, this one is 16, then 49, 32, third stage, 1, 12, 4, 49, 32, and the last stage is 1, 24, 1, 49, 32. And this is going to be the new shape for our query, key and value. So key and values are also going to have the exact same shape. Okay, and now we can see the advantage of using this rearrange function from the Einstein operation library, that we can easily convert this shape to this one. Okay.